Hello, business analytics students. In lesson 1.2, you're going to learn about descriptive statistics and visualizations. You have learned about both of these elements in statistics, which you took previously to this course. However, in this lesson, we're going to learn new types of descriptive statistics and also some more advanced ways that you can improve your visualizations. We're going to start in this video with learning outcome 1.3, which is on descriptive statistics. Specifically, it's on calculating frequency distributions, mean, median, mode, standard deviation, which you know from your statistics class, but also some new statistics like kurtosis and skewness. So first, we're going to do a review of the statistics we already know. Descriptive statistics are key to descriptive analytics. If we think about our three main areas of analytics, which are descriptive, predictive, and prescriptive, descriptive statistics is about looking at what happened. When we talk about what happened, we need to be able to analyze our large amounts of data. Depending on the type of data you have, you can calculate different descriptive statistics. If we look at our data set that we're going to be using in this lesson on different transactions, we have many different variables. We also can call these variables fields or attributes, like we learned in the first lesson. For these different variables, we also have many different rows. We can call the rows records or cases. So in this case, we want to be able to go through all the different variables and identify if we have categorical data or if we have metrics. The reason that this is important is the type of methods you use for descriptive analytics differ depending on if you have categorical information or if you have actual numbers, which are metrics. So if we do a quick review from last class, customer ID would technically be an identifier variable, which is a special type of categorical variable. An identifier variable just means that it is unique for every single person, so you won't have the same one. The region is categorical. Payment type is in text, it's categorical. Transaction code is something that looks like numbers. Usually numbers are metrics. However, a transaction code, like if you think about codes for like Amazon or any other big website where you might make a purchase on, it has to be unique for every single purchase you make. So this is actually another type of identifier. Not only do they give an identifier to every customer, they also give an identifier for every single transaction, every purchase that you make, so they know like what your order number is, for example, so they can look it up. The source of the purchase is categorical. The type of product, we're only dealing with DVDs and books in this data set, is also categorical. Time of day would be a metric because it is measured with numbers. And all of these following, amount, the tax, the total, and the number of items you purchase are also metrics. Even though number of items is something that can be counted, it's just a discrete metric rather than a continuous one, but it still is a metric. So we have a variety of data in this transaction data set. The reason that this is important is for the data that is categorical, something like product or source, the only way that we can analyze that categorical data is by looking at frequencies. We also call the frequency a count. If you want to display a frequency as a percentage instead of just a basic count, you would take each of the individual counts and divide by the grand total number of items, and that's how you get the percentages, which you can also display individually or in a table. And another way you can represent the percentages is as a cumulative percentage, where you add categories like as you go throughout a table so that you end up with 100% of the data reflected by the time you get to the last category. Those should all be familiar from your statistics class. For metrics, there's a lot more you can do with that type of data. You can calculate measures of center, like the mean, which is the average, the median, which is the middle number, or the mode, which is the most commonly occurring. You can find measures of spread, like the standard deviation. The standard deviation is basically a way to capture an average of the deviations, where deviation just means how far every single value is away from the mean. The variance is just the standard deviation squared. It's not commonly used because it would be reflected in units squared. What I mean by that is if something like the mean and the standard deviation are measured in dollars, the variance would be measured in dollars squared, which doesn't always make the most sense. The range is the maximum value minus the minimum in a data set. Then we also learned about the interquartile range in statistics, which is your third quartile of the data minus the first quartile. The interquartile range can be helpful if you have outliers in your data set, which are extremely large or extremely small values. We also have a couple of new ones for Learning Outcome 3.1.3, which are the skewness and kurtosis. Those are both measures of shape. So they describe the shape of the distribution, and specifically, they're used to compare your distribution to the normal distribution. We're going to learn more about those by the time we get to the end of this video, and they are the new ones to this course. Before we get there, we'll do a quick review of the methods we already know from statistics. The easiest way to find frequency distributions with counts and percentages is to use a pivot table in Excel. You could also use formulas such as like COUNTIF and SUMIF to build tables on your own, but it's a lot easier if you use the pivot table method because it will automatically capture all the categories in your data as well as the counts. So we'll do a couple of examples. In the first one, let's find the frequency distribution for how many sales are made in each region. So if I look at my data here, I've got the regions and I want to find how many sales are in each of them. Step one for using the pivot table is to go to the Insert tab on the main ribbon, and I'm going to insert a pivot table. You have to be a little bit careful here because I have the titles up at the top. Excel does not automatically sense the range correctly. You have to select all the variables yourself, only starting in row 5 all the way down to the bottom of the table because, like I said, Excel did not pick up the right range automatically because it incorrectly included the titles and the variable identification. For where I'm going to place the table, I'm going to put it right under where it says find the frequency distribution, and I'm going to make sure to put it in column B, not column A. If I put it in column A, it will erase the text underneath. So by shifting it over to column B, you should be able to fit both. Then, if I want to see the category for the region, I'm just going to check the box for region. And if I want to see how many sales are made in each region, I can just take the region again for a simple frequency distribution and drag it into the values. Then it shows me the count of how many times each region appears. That means how many sales there were in each region. If you want to change the appearance of a pivot table, you can do that in the Design tab, where you can pick from any of the different colors. This workbook has a lot of dark blue for examples, so I'll choose one of the darker blue colors for my pivot table. Just finding one that looks dark but still easy to read. If you want a relative frequency distribution, that means using percentages instead of counts. You can make a pivot table in almost the same way. Again, step one is I'm going to insert my pivot table, double check that the right data is selected, and then put it in this worksheet. Sorry. So I'll place it again, starting in column B, so I don't erase the text in column A underneath, and press OK. For this one, it's going to be relative frequency distribution for the product type, and there's only two products, books and DVDs. If I drag product again into the values, that's how you get your simple frequency table. To turn these into percents, you don't have to do the calculation yourself. You can simply go to your values and change the value field setting over to show values as a percent of the grand total. And that's how we can change it from a count to a percentage, and this would be the relative frequency distribution. Again, if I want to change it so it's the same color as my last one, I'll just go over to the design and change it over to a dark blue color. Finally, to combine the two that we did previously, what if you want a frequency distribution that shows how many sales are made by region and product? So for example, this one should show like East, North, South, and West, as well as book and DVD sales. Step one, I'm going to start with my pivot table. Make sure that the data is correctly selected. You could also name the range for where the table of data is located, so you don't have to keep selecting it every time like I'm doing here. That will save you a bit of time if you just name the table. Oh, and it's trying to erase my work here in the table below. So you might just want to, for now, place the pivot table just a bit off to the side, and then we'll move it into the correct position once we have the final pivot table finished. So I'll just place it off to the side so we have more blank area to work in. Then I'll put the region. So the exact same table as my first one, but this time I also want to add in the product as well. If you just check the box for product, Excel will automatically put it in the rows as well. But then it says book DVD, book DVD, book DVD like 4 times, which is a bit of a waste of space. What I can do instead is put the product into the columns. Then it forms what's called like a 2x2 table, where how you would read it is that each number, like this one, 56, is the intersection of the two values. So book and east. So that would be the sales of books in the east. Whereas a number like 37 would be the sale of DVDs in the south. These numbers here would be the total for each region. So east, north, south, west. These would be the total for each product, book and DVD. And this is the total of all sales together. You could technically also change the order to put products in the rows and east, north, south, west, the region, in the columns. But typically it's recommended for whatever variable has less categories, product only has 2, to put that one in the columns. Then it will look nicer in general. So that's always the recommendation. Whatever one has less, put it into the columns. Oh, it's just saying I have to move the other one first, but it's freezing, so I'm just going to redo some of it and put it back to the way it was. There we go. That's the generally recommended easiest way to read it. The one with more categories in the rows, the one with less categories in the columns. Then I'll move it into the correct position. And again, just change the color to match the others. Now we've made a regular frequency distribution, a relative one that shows the percentages, and a 2x2 table that shows both variables at once. Those are the most common ones you'll need to remember from statistics in order to make tables and later on visualizations in the business analytics course. For your metrics, so for actual numbers, there are lots of different statistics you can calculate. We won't even talk about all of them in this course, but we will review some of the most common. The mean is a measure of center. It is the balance point or average for a data set, and the formula for it is average in Excel. You learned that one in your statistics class. The standard error is a measure of spread. We use the standard error when we were calculating confidence intervals and hypothesis tests. It's actually your standard deviation over the square root of the number of numbers in a data set, and we learned that in statistics as well. The median is the middle value in the data set when you put them from least to greatest. The formula in Excel is median. We've learned that one before, as well as the mode, which is another measure of center, but it's the most frequently occurring value. The formula for it is mode, and we learned it in statistics. Then we have a couple measures of spread. The standard deviation is how far each of the values is from the mean. That's called a deviation. And then we basically find an average of those values. Remember that there are different formulas depending on if we have a sample or a population. The formula is stdev.s if you have a sample, or stdev.p for a population. We learned both in statistics. The standard deviation squared is called the variance, and it also has 2 versions. var.s for a sample, or var.p for a population. The ones that are new to us, so that's why they're appearing in red, we did not learn them in statistics, are the kurtosis and the skewness. Kurtosis basically measures how peaked a distribution is versus flat in comparison to the normal distribution. And skewness measures how symmetric a distribution is. You might remember in statistics, we learned to describe distributions and we'd use words like left skewed or right skewed, or you might have called them positively skewed and negatively skewed depending on your professor. But there actually is a value you can assign to how skewed a distribution is, again in comparison to the normal distribution that is perfectly symmetric. And there's a formula for that in Excel called skew that we'll be talking more about in a minute. The range is also a measure of spread. That's just the difference between the max and the min. It doesn't have its own formula in Excel, but it's easy to calculate using max minus min. The minimum and the maximum, respectively, are the smallest and largest values in a data set. Some other general statistics we calculate for a data set can be the sum, which is just equals sum, adds all the values together in a data set, and the count is very important. When you're finding other statistics like the average, you'll use the count in the data set. The count is equals count if you have numbers, or count if you want to count categorical data that's represented with words, then you need to use the count formula. So as a quick recap, to calculate some statistics for the amount variable, we have the amount variable here in column Y of our table, and we want to find the mean, median, mode, standard deviation, max, and min for that variable. In order to do that, as a quick recap, I would just use my formulas like equals average is for the mean and select all my values. The range will be Y6 to Y477. To speed things up, I'll copy that value so I can use it in other statistic calculations. The median on the same range, Y6 to Y477, I get 20.61. And for the mode, I get 1533. If I want the standard deviation, you have to be careful about which formula to use, thinking about if this is a population or a sample. This should be a sample data set. It's only 400 values. Hopefully a company would have more than 400 sales in its lifetime. This should only be a small piece of all the sales, and it will be on the same region, the same cell references from Y6 to Y477. The max value is they sold something worth $247.14, whereas the minimum amount of a purchase was only $15.08. If you wanted to find the range, it would be the difference between the max and the min. So it's a pretty large range of $232.06. Finding descriptive statistics in this way is pretty quick, but it can be a little bit repetitive when you have to find descriptive statistics for multiple quantitative variables or metrics. What I mean by that is it didn't take us too long for just amount, but what if we had to repeat the same steps again for tax, total, number of items? It would get a bit repetitive. So one way to speed this up is by using the descriptive statistics tool found in Excel. What the descriptive statistics tool does is it calculates all of the different statistics I put in this table all at once. And what's cool about it is it can calculate them for multiple variables at once too. It could find all of these values for amount, tax, total items, etc., all at the same time. The only thing you have to note about using the descriptive statistics tool is it's built for sample data, not for population data. So for things like the standard deviation and the variance, where it matters what formula you're using, the descriptive statistics tool will always use the sample formulas. It will never use the population formulas. There's a short video here that shows you how to add in the tool if you don't want to watch this whole long video for the learning outcome, but I'll also show you how to do it here. If you go to the Data tab, you'll see I have this button, Data Analysis. But if you don't previously have that from using Excel in the past, how you get that button to appear is you have to go to File, then Options all the way down at the bottom. After you select Options, you'll go to Add-ins. And where you see this Manage Excel Add-ins, press Go. This is where you can turn on the Analysis Tool Pack, and you can turn on Solver that we'll use later in the course as well. Both of those tools can be turned on. If you don't have them checked, just simply click in the box for both and press OK. Once you've done that, if you click on the Data tab, you should have the button for Data Analysis. Once you click on the button, you'll have a number of statistical tools that we'll be using throughout this course listed. They are listed in alphabetical order. The one we're looking for is called Descriptive Statistics, so it should be near the top since they are in alphabetical order. Once I select it, I'll see this box where I'll have to input information in order to get the descriptive statistics I want. First, for the input range, this is where you're required to select variables that have quantities, that are metrics. I want to find my descriptive statistics for amount, tax, total, and items. So select those four all the way down to the bottom. So I've included all values for the variables. You have the option for how the data is grouped by columns or rows. This is just the orientation of the data set, and in this case it's grouped by columns. Each variable is in its own column, Y, Z, A, B, etc. I have to check the box for labels in the first row because I selected the words amount, tax, total, items. If I did not select those words, then I would not check the box for labels in the first row. However, it's always best to select the words because if you don't select them, then in your final output for the descriptive statistics, it won't tell you which values go with which variable. So you should always select the text for the variable names so you know which values go with which variable. For the output range, I'm going to actually switch it. There we go. So that it appears here. If you don't select this, by default, it will go into its new own worksheet. So I'll make a new sheet just for the descriptive statistics. And you have to check the box for summary statistics because that's what we want it to calculate. Like the mean, median, mode, all those summary statistics. And press OK. And here are my statistics. Like I said, it gives you every single value that I listed in the table here. But it gives you it for more than one variable at once. So when I use the individual formulas for just the amount, I have to do 6 different formulas to get just 6 of the values. This gives me all of the values for amount, tax, total, and items as well. So it's a fast way, nice way of getting multiple descriptive statistics if you have lots of variables to analyze. So I do recommend using that tool in that case when you have lots of variables. And that is it for the descriptive statistics tool. Now that we've learned that tool, as a quick recap to how we can find some of our values from statistics like the mean, median, mode, range, all those ones that we commonly calculated, we need to talk about the new ones that we're learning in this course. Specifically, the kurtosis and the skewness are the ones that we have not learned previously. So I'm going to talk more about what these values are and how you can interpret them. So what do the values that we got for the skewness and kurtosis actually mean? So first we're going to talk about skewness or skew. It measures the degree of asymmetry. So what I mean by that is the normal distribution is supposed to be a perfect bell-shaped curve. I know mine might not be perfect because I'm drawing it freehand, but it's supposed to be perfectly symmetric on both sides. So it has like a mirror image appearance to it. That means it has perfect symmetry. But not all data sets, when you make a picture of the distribution, will have that perfect symmetry. If they are perfectly symmetric, like the normal distribution, then what we call the coefficient of skewness, or CS for short, would be equal to 0 exactly. But, as I mentioned, most distributions are not perfectly symmetric, like an exact normal distribution. In statistics, we learn to describe the direction of a skew. If you have a curve that looks like this first one here, where we have a tail appearing on the left of the distribution, that tail means you're stretching towards some outlying values. We call that a left or a negative skew. In that case, if you have a left or a negative skew, then the value for your coefficient of skewness should be a negative number. The higher the negative number, the bigger the skew is. So if you have anything like less than -1, you have a very skewed distribution like this one. If you're getting closer to 0, it's looking more normal and just has a small skew to the left. On the other side of things, if your tail is on the right side of the peak, like this one, we call that a right or a positive skew. And in that case, the coefficient of skewness would be a positive number. Just like for the negative ones, anything bigger than 1 as a number for the coefficient of skewness, we consider a high skew because 0 would be the perfect symmetry. So the closer you get to 0, the closer you get to symmetry. Anything bigger than 1, you consider a larger positive skew. The other new value is the kurtosis. If for the skewness you're looking at the tails, so for what side the tail is on and how extreme that tail is, the kurtosis is instead looking at the peak of the distribution. In green here, you have the normal distribution, what a perfect bell-shaped curve should look like. But sometimes we have curves that are more stretched out, or what we call more peaked, and sometimes we have curves like the blue one that are more flat, like almost they're pushed down from the normal distribution. And that's what the kurtosis describes, basically how peaked or flat the distribution is in comparison to the normal distribution. Just like for the skewness, we have what's called a coefficient of kurtosis, and if that coefficient is 0, then you have a perfect normal distribution. If your coefficient of kurtosis is a negative number, then you have what's called a platykurtic distribution. Platykurtic is just a fancy way of saying more flat. It's more short or flat topped than a normal distribution. When you have a distribution that's shorter or more flat topped, it also means that you have fewer outliers. You can see that the blue one comes down a bit closer to the x-axis than the normal does. So technically that would mean fewer outliers, or what they call lighter tails. On the other side of things, if you have a value for the coefficient of kurtosis that's greater than 0, you have what's called a leptokurtic distribution. Leptokurtic is just a fancy way of saying more narrow or high than a regular normal distribution. And in that case, if you look way down here, you can kind of see the red curve coming out higher than the green normal one. That means it has heavier tails than the normal distribution or slightly more outliers. You can see that there are various degrees of kurtosis in this little table, that if you have exactly 0, it would be normal, but between 0 and -1, it's only slightly platykurtic, which would mean flat. Between -1 to -3, it's moderately flat, or less than -3, highly flat. On the other end, if you go between 0 and 1, you're slightly leptokurtic, which means slightly peaked. I had a typo here that is corrected. If you're between 1 and 3, it'd be moderately leptokurtic, which is moderately peaked, or greater than 3, then you would be highly peaked distribution. So if we want to think about these measures, the kurtosis and the skewness, for some of the variables that we calculated them for example, let's look at the amount, so these two numbers here, and the items, kurtosis and skewness. What do these values actually mean? Well, if you want to get a good idea, it's good to make a picture first. So to make a picture to see if you can see any noticeable skew, or if you can see if you have like a big peak, or if the distribution looks more flat, step 1 is to make a histogram. So to make that histogram for amount, all I would have to do is scroll over to my amount variable, and then I'm going to make sure I can see where I want the histogram in that area, and on the Insert tab, insert my histogram. And this is what it looks like with no change to the settings at all. So in this case, you have one gigantic high bar, and then all these little bars off on the right side. So this is obviously showing a big right skew. If we want to see if the skewness matches that, you can calculate the skew with equals skew. And I'll select all my values for the amounts. I get 2.612. To check that, if I look at amount skewness, 2.612 is also what I got with the descriptive statistics tool. So I just wanted to show you that the numbers are the same, whether you use the tool or if you use the formula for skew. For the kurtosis, this one has like a super tall bar in comparison to these like very, very, very small bars. In that case, because it has such a tall one in comparison to the others, that's showing that it's probably leptokurtic, which means very, very peaked in comparison to the normal distribution. Because for a normal distribution, the bar in the middle shouldn't be so much taller than the others. But to check it, let's calculate the kurtosis. Equals kurt is the formula for the kurtosis, and I'm calculating it for my amounts. I get 5.1822. If I look at my table, anything bigger than 3 is considered highly leptokurtic, which means highly peaked. So the kurtosis is saying we have a highly peaked distribution, and the skewness, because it's bigger than 1, is saying you have a high positive skew for this distribution. So in the interpretation, I would write that the skewness shows high positive skew, and kurtosis shows highly peaked, which does mean heavier tail with more outliers. And again, you can look in the table for that. Kurtosis, anything bigger than 3 would be considered highly leptokurtic, highly peaked. Heavier than normal tails, more outliers. We'll do another one for practice for the items. For items, I can select the data first and make a picture of the distribution. Insert my histogram, and it looks pretty similar to the amount distribution, even though the values are on a completely different scale. What I mean is that it has one really, really tall bar for people only purchasing 1 or 2 items, and then very small bars for people that purchase many, many more items. For the skewness, I'll use my equal skew formula, and the items are found over in column AB. And then I'll do the kurtosis as well, using equals kurt, and selecting my values over in column AB. I get a value of 2.568 for the skewness and 5.005 for the kurtosis. Let me check that those match. And they do match the values we found in our descriptive statistics tool. Just like for the amount, the skewness is positive and it is a number much bigger than 1. So the skewness shows a high positive skew. And the kurtosis is way bigger than 3 and it's positive. So that means it's highly peaked or highly leptokurtic because it's bigger than positive 3. Again, meaning it has heavier tails and more outliers than a normal distribution would have. So altogether, the high skewness and high kurtosis means heavy tails with more outliers. Both of these have very similar shapes with high positive kurtosis and high positive skewness. So I wanted to show you an example that looks closer to the normal distribution. So I made an example data set. It is simulated to be close to the normal distribution, just so I could show you what a data set close to normal might look like and what the values might be like for the skew and kurtosis. So in this case, if I make a histogram, it doesn't look perfectly like the normal distribution, but you can see it looks a lot more like a regular bell-shaped curve than the other ones do that have the one super tall bar and the very, very small bars on the right. This is my example for being approximately normal. If for a data set like this one, you find the skew and you find the kurtosis, notice that this time the values aren't so large. A skewness of 0.13, it is a positive number, and it's somewhere between 0 and 0.5. So it's a slight positive skew, almost 0. It's close to the normal distribution. For the kurtosis, 0.0288. That kurtosis is very, very close to 0, close to the normal distribution. So Both values are close to 0, which means they're close to the normal distribution. No large skew or peaks. So it's pretty close to the normal distribution. Why do we go through the trouble of finding the skew and kurtosis? You might remember in statistics that some of our conditions for using certain statistics were that you should have an approximately normal distribution. There's a nearly normal condition. If you can calculate values like the skewness and kurtosis for a data set, it can help you to see if your data actually is nearly normal or not. For something like amount and items, these are not nearly normal. For this example data set, that's an approximately normal distribution. This would be considered nearly normal because it has a small skew and a small kurtosis value. One other thing I wanted to point out is that if you look back in the descriptive statistics table, there's a reason I didn't find the skew and kurtosis individually and made graphs for the amount, tax, and total. What do you notice about the values for the kurtosis and skewness for amount, tax, and total? You should notice that those three, I'll change this one to a different color because it's different, but for amount, tax, and total, the values are all the exact same. So the reason the values are all the exact same is because of how we calculate the tax. The tax is just 13% of the amount, and multiplying by a constant number like 13% doesn't change the shape of the histogram. The shape of the histogram would still be the same, so the skewness and kurtosis stay the same. For how you calculate the total, you could just do times 1.13 to find the total amount spent. And again, multiplying by a simple number like that is a simple transformation that won't change the shape of the histogram. So when the histogram shape does not change, it doesn't change the values for the skew and kurtosis. So they would actually be identical for amount, tax, and total with no changes. So these three values are simple transformations. Multiply by 0.13 for tax and 1.13 for total from the original amount. These just scale the data, but don't change the shape of the distribution. So we'd have our same skew and our same kurtosis. And that is it for our discussion of skew and kurtosis. A couple more descriptive statistics that the textbook talks about specifically that I will also mention because, again, they are new to you is one is called the mid-range. It's another measure of center that just takes an average of the maximum and the minimum in a data set. So it's different than the median, the mean, or the mode, but it's just another way to capture where the middle would be. But if you have your data set, we have our max, we have our min. The average, the median, and the mode might not be exactly in the exact middle. The mid-range, because we simply cut it in half, should be exactly in the middle. We'll cut it in half. It's pretty easy to calculate. If I want to find the mid-range for amount and items, what I would do is for amount, I do my max of Y6 to Y477. Again, I'll calculate that or copy that cell reference so I don't have to keep typing it out. Minus the min of that same range. I'll put brackets around the whole thing so that I make sure I'm dividing the difference between the max and the min by 2, not just the min or just the max by 2. And I made an error here. It's supposed to be plus, not divide, not minus. I typed in minus because I'm used to doing the range. But in this case, you add them together and divide by 2 to find the exact middle between the max and the min. So I just need to correct that to a plus. And that gives me my mid-range. So for the amount, I got 131.11. And if I do the same thing for items, I'll start with a bracket so I can make sure the order of operations are done correctly. First, the max of my number of items. Again, I'll copy the range so I don't have to type that all in or select it all again. Then I will add on the minimum and divide by 2. And I get 650. And that's the mid-range. It's just another way to capture the middle of the data set, or what we call a measure of center. Another new descriptive statistics is called the coefficient of variation. Both the mid-range and the coefficient of variation are useful values, but they're not included in the descriptive statistics package. I think part of the reason that they're not included is because they're easily calculated using other values that are given in the descriptive statistics output. For example, the mid-range can be found using the max and minimum. The max and minimum are given to you in the descriptive statistics. Similarly, the other new one we're learning, the coefficient of variation, can be found using the standard deviation and the mean. So as long as you have those two numbers, it's easy to calculate it. What the coefficient of variation does is it's a measure of spread that captures the relative dispersion in a data set. Why this is important is because if you have two variables measured on completely different scales, it can be hard to see which one has more variation. For example, something like amount has a really big range of values because the difference in prices is like hundreds of dollars, whereas the number of items, it's on a smaller scale, only from a max or minimum of 1 to a maximum of 12. So the range is only 11 instead of hundreds. But just because the range is smaller doesn't mean that it necessarily has less variation overall. In order to see if it has less variation, because items is just a count and amount is measured in dollars, the coefficient of variation gives you basically a proportion of the standard deviation relative to the mean, so you can see which variable has more dispersion regardless of what units is measured on. The higher the value you get for the coefficient of variation, the more variation you'll have in your data set. The lower value you get for the coefficient of variation, the less variation you'll have. We can calculate them for our amount and items so you can actually see for yourself what the values are interpreted as. So std.s is the first step. I'll do the standard deviation of the amount. Then once I have that standard deviation, I'm going to divide it by the mean. And again, it's that same range. Just copied the wrong one. Y6 to Y477. Oh, whoops. I was looking at the text-based formula, but in Excel it is average, not mean, for the formula. There we go. 1.43 is the value I get for my coefficient of variation. That should actually have no units because both the standard deviation and the mean are measured in dollars, so the dollars will cancel out and it will be a unitless quantity. For items, again, I would also do the standard deviation.s, but for the range for items, which is AB6 to AB477, then divide that by the average, again, of AB6 to AB477. And I get 1.358 approximately. So with these two values, what we can see is that the coefficient of variation is smaller for items and bigger for amount. That means amount has a little bit more variation than items. They aren't like completely different because both are 1 point something and you could get a value that was way higher than that, but you can see that the amount does have more variation. That isn't obvious from just looking at the mean and the standard deviation by themselves because they're measured on completely different scales, like I said. This one is in dollars, this one is a count of items. So you can't tell that just from looking at these numbers. So which variable has more variation? The amount has a higher value for the coefficient of variation, so it has more variability, or you could write variation there, whatever way you prefer to describe it. And finally, another type of descriptive statistic is the z-score. You've learned z-scores before. We calculated them for the normal distribution, But we didn't often calculate them like for an entire data set to use them as a descriptive statistic. We did them for a specific purpose, for probability calculations from the normal distribution. So I just wanted to quickly show you, it's an example in the textbook as well, that you can use z-scores to figure out how far away an individual observation is from the middle, the mean, and you can use that to help you find outliers. Any outliers in the data set would be considered those with z-scores bigger than 3 or less than -3. I'm only going to find them for amount because it does take a bit of time. You don't really need to do it twice for amount and items, but I'll calculate them for amount and show you how the z-score calculation works. So for my z-scores for amount, you could do the formula individually, which is you take each individual value minus the mean and divide by the standard deviation. But another way to do it is you can use the formula called standardize, where you would take each value, then select where you've already calculated the mean and standard deviation, instead of doing the formulas individually. So for the amount variable, I already calculated the mean here and the standard deviation here. The only thing you need to be really careful about is using absolute cell references. You have to lock in where you found the mean and the standard deviation. Otherwise, when you try to find the z-scores for the entire data set, those values would keep changing. They'd keep going one down, one row down, one row down, and then they wouldn't be the values for the mean and standard deviation anymore. So you just have to be careful to lock those in. Once you've done that using your absolute cell references, you can use the fill handle to automatically fill in the whole column. There we go. And you could look for any numbers that are bigger than 3, like this one. This would be considered an outlier, where the person spent $244.50. But the data set is fairly large, so it's hard to see exactly where all the values that exceed 3 are. Here's another one. So if you want to speed things up a little bit, what you can do is you could select all of your z-score column and add conditional formatting. For conditional formatting, we could say we want to highlight any value greater than 3 in a red fill, so it will stand out, and also any value less than -3. And then if I scroll through, my values that are outliers should now pop out in the bright red. So I can see all my outlying values. All of them are positive numbers that I'm seeing, which means that when we have outliers, it's for the people who spend a lot more than everybody else, that there's no outliers for people who spend a lot less. That's what the positive z-scores mean. It's people who are spending more than the average. That's why they're showing up as outliers in the data set. A lot more than the average, 3 standard deviations more. So the z-scores can actually also be used as a descriptive statistic, not just as a tool for normal distribution calculations, to look for outliers in your data set, which corresponds to what we were talking about here as well too, with the skewness and kurtosis, that we saw that things like the amount will have more outliers than a normal distribution, and we did see quite a lot of outliers when we used that conditional formatting to highlight them in red. The last thing to review and talk about from your statistics course that will be useful for this course is that you can also calculate statistics within a pivot table by changing the value field settings. You can calculate things like averages, minimum, maximum, standard deviation, and variance. And you can do the standard deviation and the variance for either a sample or a population, all within a pivot table. So in order to do that, what I'll do is an example where I use a pivot table to find the average of the amount and standard deviation of amount for each product. So step 1 is to make the pivot table. So I'm going to insert a pivot table. Again, the region isn't showing as correct because of the titles, so I have to update that. And I'm going to place it over in column B again and press OK. Then I want the statistics for each product. So I'll put my product in the rows. After I've put the product in the rows, I want the average amount spent on each of these. So I'm also going to check the box for the amount. By default, it's showing me the sum of all the money spent on books and all the money spent on DVDs. But I don't want sum, I want the average. So how I'll change that is in value field settings, I'll switch it over to summarize values by the average. And this will now be my average amount spent per book and DVD. I'm just going to format it as money. If I want the standard deviation of those amounts as well, to say, okay, this is the average, but this is how much it varies by, I'll also put the amount into the values again, and again, change it from showing sum, but this time to showing standard deviation. STDDEV is for the regular sample standard deviation, whereas the one with P on the end would be for a population. We discussed that we have a sample here, so I'll use the first one, just STDDEV. And this will give me the standard deviation of my amounts. Again, I put them in accounting format just so that they're formatted using dollars. So we can see books sell for $56.22 on average, but they have a really high standard deviation of $73. So it means books can be very inexpensive or very expensive on the other hand. Whereas DVDs sell for an average of $19.82, but have a standard deviation of only $2.82. So that shows there's very little variation in the price of DVDs. They're all pretty consistent around that $20-ish mark. And that's how you can use a pivot table for descriptive statistics as well. So in this learning outcome, we did a lot of different work. We did a review of using pivot tables for frequency distributions. We did a review of just the basic formulas for descriptive statistics. We used the descriptive statistics tool to calculate many descriptive statistics at once. And then we learned some new descriptive statistics like the skewness, kurtosis, mid-range, coefficient of variation, and z-scores to look for outliers. Finally, we went back to the pivot tables to talk about statistics within the pivot table. This is an essential learning outcome because next we'll need to use a lot of these pivot tables and other tools in order to create visualizations for our data sets, which we'll do in learning outcome 1.4. Thank you.